I'm going to go ahead and start an intro, and I see more people kind of starting to filter in. So, again, I'd like to just welcome everybody back to what is now the penultimate seminar in the Idaho Water Resources Seminar Series. As a quick reminder, there's not going to be a seminar next week because we'll be on fall break at the universities, but we will be back on December 2nd. So anyhow, I'm going to go ahead and introduce Tom and Erin. We've got Tom Points, who's the Senior Public Works Director for the City of Nampa, who leads a diverse team on providing essential services, including transportation and water utilities. Tom previously worked at Idaho and Washington Departments of Transportation and as a geotechnical consultant, and holds a bachelor's in science and geological engineering as licensed civil engineer in Idaho. Then the other person I'll introduce is Erin, who's an environmental engineer and currently serves as the Northwest Water Resources Strategic Growth Leader and Idaho Client Account Manager at Jacobs Engineering. Erin has a BS in biology and a master's in water resources and environmental engineering and a PhD candidate in biological design. So again, thank you both for providing the seminar today, and I'll let you take it out over at this point.
Okay, well, thank you for listening to our presentation. We're glad to be here. So Aaron and I are going to take turns on this presentation. I'll kick it off so you can see the overview here. So we can talk about contaminants of emerging concern. So things like PFAS and medications in water, pollutant and pathogen removal and different media to do that. Examples of some wetland projects, Karcher wetland, which we're designing here in Nampa, and then water quality modeling and design features. So let me just kind of, so we are looking at to construct a constructed wetland here in Nampa. It's within the city limits. It's over by we call it Karcher Interchange because if you're familiar with Nampa, it's just right next to the Karcher Interchange on the I-84. And it's along Indian Creek, and it's fairly close to our water treatment plant. It's about a mile downstream. And Indian Creek is a tributary to the Boise River, which ends up in the Snake and on down into the Columbia. So it is a waters of the U.S. And um, so we this is a very innovative project, and we're looking for different ways to uh, treat water for water quality and also on water temperature. It's been getting a lot of attention on this project because of the unique media that we're going to place in the wetland, and that there are carbon sources, which is we're not we think we're the only one in the U.S. that's going to build something like this scale. We haven't been able to find anybody else working on this type of project with carbon. There's a lot of science behind the carbon, a lot of engineering behind the carbon. The wetland is very unique. It's not just a cattails wetland like you usually think of a wetland. It's going to be has some really awesome, beautiful engineered features in it, which Aaron can tell you about. So I think I'll turn it over to Aaron here and let her, and I'll come back and talk about why we envision this project in Nampa.
Thank you, Tom. So you can see in these pictures here on the overview slide, that is actually the site of the future wetland. We have been fortunate enough to give tours to a lot of different parties who are interested in this project, but you can see what a beautiful site it is. And with this constructed wetland, it's only going to be more beautiful and an even greater community asset. So I'm going to give a little bit of an overview about contaminants of emerging concern and constructed wetlands. Many of you know what these are, but just as a quick overview, when you have a contaminant of emerging concern, it's something that doesn't have a regulatory standard associated with it yet, but there's enough science to indicate that it has some toxicity and it's harmful to humans or wildlife. Sorry that my camera is going out of focus there. Sorry about that. Um, there are a lot of different things that are not regulated yet, like pharmaceuticals. So things that are not treated through the wastewater treatment process. Same thing with personal care products, all the different body washes and different things that we use in our showers every day. The one that everybody's talking about is PFAS and PFOA, also termed forever chemicals. 6-PPD quinone is one that you may or may not have heard of. It is a tire constituent that is known to be extremely toxic to fish. I'll talk a little bit more about that in a minute. PFAS is such an interesting chemical because it is just so darn useful. It was put in so many different products because of its ability to repel water and withstand heat due to the really strong carbon-fluorine bonds. The problem is because it takes so much energy to create these chemicals, they are in everything from, Gore-Tex clothing, nonstick cookware, fast food packaging. They think it's in makeup, all kinds of things because it's so useful. Waterproof, flame-proof, but it is persistent. The same characteristics that make it so useful also make it very harmful to humans because they don't break down. So basically, right at this point in time, there was a national ambient water quality criteria proposed for specific PFAS compounds, and there is a drinking water criteria, but the problem is there are so many different PFAS constituents. It's not just one chemical. It's over 10,000. Well, some models have predicted up to 60,000 different chemical structures. So it's really hard to regulate. I mentioned this one, 6-PPD quinone. We just discovered what this was. The University of Washington did some research and around the early, 2020, 2021 timeframe. They kept having coho salmon fish kills in the Puget Sound, and they couldn't figure out what it was. So the University of Washington partnered with citizen scientists, and anytime people saw a fish kill, they asked them to call this particular hotline that they'd set up. And the University of Washington would send a bunch of grad students over. They would take samples and put it in the mass spectrophotometer. They did this enough times and they kept on seeing a specific spectral characteristic, which led them to understand that this is a constituent called 6-PPD. And when it is in nature, it becomes 6-PPD quinone, which is extremely toxic to coho salmon, with acute mortality happening at levels as low as zero point 0.1 parts per billion. And it's really ubiquitous in stormwater. If you think about any highway, especially where there's just a tremendous amount of tire wear, it's a micro pollutant, but it's all over the place. And anytime there's a storm event is when they would have these big fish kills. So now we know what it is, and they're trying to get it out of new tires. But as of right now, it is still in all tires produced in the United States. It is beneficial, kind of like PFAS chemicals. It has a purpose, which is it makes tires wear better and prevents them from becoming hard, so it keeps them safer. But the downside is that they are extremely toxic. This compound is extremely toxic. So these different toxic chemicals has really pushed the need for different types of treatment systems. The good thing about 6-PPD quinone is that it has been proven through a lot of pilot studies to be treated effectively through green stormwater infrastructure. So in the state of Washington right now, they are really pushing to have any highway that drains to a water that has threatened or endangered species or the cold water fish to have some type of natural treatment system before it goes into that river. Because we do know, like I said, that natural treatment systems are very effective. So what is a treatment wetland? You are all familiar with wetlands, but a treatment wetland is basically using those natural plants, those natural systems, the biology, the geochemical, everything that happens in a wetland and harnessing it using specific design tenets to make sure that it can accomplish what you want it to. It's really interesting when you think about a wastewater treatment facility and a natural treatment system like a constructed wetland, and they have a lot of the same components. So through these different cells, different type of treatment occur. When you look at the wetland benefits, there's obviously some great water quality benefits. I'm going to teach you a lot about that today. And even when there are no engineering, the facilities added, a wetland is really good at retaining sediment and doing some nutrient cycling and uptake into the plants of different contaminants. Wetlands are really great at flood mitigation and aquifer recharge. They're amazing for carbon sequestration. It's said that 81 to 216 metric tons of carbon can be sequestered per acre. A little bit of improvement in air quality, but of course, habitat is tremendously improved, especially for, like if it's in a natural waterway, you can have, it's great fish habitat, invertebrate, all types of habitat. But plus, wetlands are beautiful. They are a tremendous community asset, and they are something that, people like to look at. They're birds. There are different things that people like to enjoy. Um, they can provide a lot of economic savings. And then, they're also macro scale benefits. So this is something that I took from the Minnesota Pollution Control Agency that just talks about high level benefits of wetlands. But now I'm going to talk to you about a couple of the different types of configurations. So you've got the natural wetlands, which provide a lot of benefit, but when you engineer, you can apply the water to these wetland systems in a lot of different ways. So the wetland diagram on the left is showing a horizontal flow wetland where you apply the water in a way as so that it flows horizontally through the system. And you can get an idea there that the water is not just being treated through the sand and the gravel, but the root systems provide a tremendous amount of treatment. So you can make it flow vertically, or you can apply the water through perforated pipes on the top so that it flows vertically through the wetland, and then you have a pipe that catches the water at the bottom to bring it to the next cell. There are the free water surface wetlands. I'm just introducing you to some of the terminology that we use. And, this is very similar to a natural wetland where you've got a soil bed, you've got emerging vegetation, water exposed to the atmosphere, everything that you would imagine. These can be used for tertiary treatment. And, when you think about that, it's pretty impressive about the water quality treatment that it can occur. But the main thing that you're designing is, well, there are a lot of different parts that you're picking the media, you're picking the plants, but you're also picking the hydraulic loading rate. How much water do you apply? The hydraulic residence time in each cell is really important because it really helps provide that level of treatment that you're trying to achieve. Now, here it says, this is from a textbook, it says impermeable liner. It depends on the type of wetland. We have wetlands that we've designed for mining operations where you do have to have an impermeable liner. But in most of our wetlands, we actually like to have infiltrate. We want it to be connected to the groundwater if there's no sources of contamination because it provides that extra cooling and that interface that is really a more sustainable natural system. And so then this is an opportunity like what I was showing earlier, where it's going to flow horizontally through the wetland, and then there's an outflow on the other side. But these are less known, and they are subsurface flow wetlands. So from the surface, it looks like vegetation and ground. And these are really remarkable because we sometimes have had these in other locations where we call them walking on water, because people can walk on top of it. What you've got here then is the water is flowing through substrate, very specifically selected substrate. So it almost works like a trickling filter in a wastewater plant underground, in a way, because there's biofilms that form on all of these different pieces of gravel and rock. So as the water's flowing through, there are a lot of different types of treatment that occur. And one of the best things is that it's really cooling, provides a lot of, protection from the ambient air and keeps the water very cold. In the Pacific Northwest, that's going to be one of our biggest challenges moving forward is water temperature because our cold water species are very sensitive. But again, the absorption that happens on those biofilms on the rocks are really a powerhouse of treatment. And what you're doing with these subsurface flow wetlands and the free water surface wetlands is you're combining them in like a series of different cells, all intended to accomplish different things. So you can have one that overflows or goes underground through a pipe to the next cell. We like to have about a 1% grade, so the water flow, and really, it's the grade that you design the bottom to have is going to really control how quickly or slowly the water moves through the system. And then I just had to put this one in there. Floating wetlands are really interesting. They provide shade, and we've used these in some really polluted mine wetlands where, again, the root systems are so effective at treatment. So in this case, you've got the biofilms and all the different organisms that live within the root systems, but then the plants also take up a lot of the material. And then you've got the benthic layer on the bottom. So again, this provides shade, it provides treatment. So these are just a lot of different configurations. So now I'm going to go into just a little more detail about the pollutant and pathogen reduction processes. So the biological treatment that occurs, there are a lot of naturally occurring microbes and vertebrates that provide treatment, just like in a wastewater system. There are bugs, and they like to basically feed on a lot of the material. Metals and organic materials can be treated through, things that you hear about in other types of treatment: ion exchange, precipitation, adsorption, filtration. All these different types of processes are occurring. And then you want both aerobic, so highly oxygenated zones, and anaerobic zones, because you've got then both oxidation and reduction occurring through the wetlands. So this is just a little bit more of a visual about the different types of treatment that is occurring. Again, one of the things you'll see in our designs is you want to have a sedimentation basin at the beginning of the wetland. That is an area where you just allow the water to be more still for a little bit of time to allow the larger pieces of sediment. Oftentimes there is phosphorus attached to that sediment to filter down to the bottom. So those are the physical processes. Organic matter, nutrients, pathogens, those happen throughout these different things that happen. The nitrogen cycles basically happening in the wetland. Adsorption, precipitation is working in the wetland for phosphorus as well. And of course, the plant uptake for nutrients is a big one. So those are the more traditional types of things that we're hoping to mitigate through a wetland process. But there are a lot of other contaminants of emerging concern that also get addressed throughout these systems. So, in our waterways, because of treated wastewater effluent, we have, and also agricultural practices, et cetera, we have things like an agrochemical like atrazine. We have residuals of different types of pharmaceuticals like testosterone, naproxen, one that we all participate in contributing, or many of us anyway, caffeine. These things, triclosan, things that we all put into our wastewater treatment facilities, oftentimes don't get treated through the wastewater treatment process, and make their way into our waterways. So when you're looking at the things that happen in the wetland, you've got photolysis, which is very good at mitigating certain constituents. And we design specific features into the wetland to accomplish that, like aeration drop structures, cascades, etc. Then when it comes to aerobic biodegradation, again, those aeration drop structures are really good for that, kind of the same types of things, but then also those free water surface wetlands that I mentioned earlier. Those are good. Aerobic biodegradation is effective for mitigating ibuprofen. Maybe many of you have taken an ibuprofen in the past month, the caffeine, estrogen from birth control pills, things like that. Plant uptake and storage is a big one, and some of those same constituents are taken up by the root systems into the different plants. And then I mentioned the root systems are really effective, and the deep media beds for some anaerobic biodegradation, and then sorption is another big thing. So just giving a little bit of detail about what's actually happening through different parts of the different cells of the wetland. But the thing that is extremely innovative about this particular wetland that Tom alluded to is there is a polishing cell. There's a lot of emerging research on this type of combination. So these media are proven to improve water quality. That is not the innovation here. The innovation is using it in conjunction with a wetland. That has not been done at full scale, like Tom mentioned. Biochar is a really interesting material. It's a carbon material produced from pyrolysis of almost any organic material. You can use things like juniper trees or even biosolids from a city, which the city of Nampa may be doing in the future. Zeolite, I'm going to tell you a little bit more about each of these materials, but I'll go back into biochar with a little more detail. Essentially, like I mentioned, you have to use pyrolysis, which means no oxygen. And what they're finding is at even higher temperatures than this, you can break down PFAS chemicals. But for this particular purpose, the biochar is just a highly sustainable product made from bio waste. And it is very highly adsorptive for both organic and inorganic contaminants. So ion exchange, hydrogen bonding, I mean, there are a number of different ways that this media is effective for purifying water. It's not too dissimilar from, like a Brita water filter, quite frankly. Zeolite's a really interesting product. It was used by the ancient Mayans to purify drinking water. So its filtration abilities have been known about for a very long time. It's a naturally occurring volcanic crystalline aluminosilicate material. It's mined here in Idaho. It can remove soluble and insoluble compounds because it has ion exchange capabilities and of course then adsorption like the biochar. It can be used as a soil amendment once it's e- either after it's used as a treatment material or even just in and of itself, it's used as a soil amendment. And actually, so is biochar. Now, granular activated carbon is very well known in the drinking water treatment industry because it's been used extensively to treat drinking water. It's known to mitigate VOCs, metals, contaminants of emerging concerns such as pesticides and pharmaceuticals. So both the volatile organic chemicals and it's also known to be effective for PFAS. And again, it's a carbon matrix, has a lot of small and large pores, which is really great for different sizes of organic molecules to absorb. So again, it's been very well proven. So I alluded to this a little bit, but there are different design considerations when you are designing the wetland. You for sure want to make sure that you've got that sediment forebay. That is one of the few places that requires regular maintenance. And it really depends on the water quality that you are putting into the wetland. It will really inform how often you have to clean that out. But for each constructed wetland, you've got a hydrologic budget. You've got that hydraulic residence time. You design it to specifically so that it spends the right amount of time in each cell. The big things you have to design around is short circuiting. People have learned a lot designing these through the years, and you don't want dead zones. So you need to make sure that if you are designing these, you work with experts who have done this before. They know how to mitigate those challenges because short circuiting will basically make it not as effective. It will bypass some of the treatment process. So it's just really important. And then again, the different cells provide different levels of treatment. Before we go back into the Nampa project, I wanted to just share a few other wetland project examples. Roseburg Urban Sanitary Authority, RUSA, has used a constructed wetland system for almost 20 years to provide tertiary wastewater treatment. It's able to remove phosphorus and cool the water significantly through this hyporheic or underground discharge. The cool thing about this is it's basically low rate irrigation on a hillside, and the wetland system basically forms kind of at the lower level as the water flows down this hillside underground. And they're able to have sheep graze in some of these areas. And it's a fascinating treatment system that has been very effective. And it's the thing that the neighbors like is that it's going to be protected and open space. That a lot of people don't even recognize that it is a treatment system. Another project is the Talking Water Wetlands. This one right now, it's been challenged a little bit. It takes water from an aluminum manufacturing facility, so industrial waste, and then it also takes municipal wastewater before it discharges into the Willamette River. Um, So it's an absolutely beautiful community asset with waterfalls and a lot of features that people don't even recognize are treatment features. Very wonderful community asset. It's ranked as the #1 place to walk in Albany, Oregon. Here's an example of a more industrial type of project where the main goal was nitrogen and phosphorus removal and temperature reduction. This is basically that tertiary treatment for the after it goes through the wastewater treatment system, hoping to also achieve some temperature reduction. But the main thing is phosphorus and temperature removal so that they can recycle this water. This is a definite more industrial facility where the wetland is intended to remove arsenic and nitrogen, and then they want to purify that water so it can be then used for aquifer recharge. This is the first constructed wetland project that I worked on a long time ago in Florida in the year 2008 to 2010. So Florida has very protective rules about the water that they put into the Gulf of Mexico because it was experiencing such tremendous algae blooms. So you can see the water flows through a series of different cells. There's a flow path that inflows here, and then it goes through this pond, and then a number of different wetland processes before the outflow. And what you can't see here is the beach is right on the other side of this. But you can see what the walkways look like. It's beautiful. There's a lot of aquifer recharge that happens here. This part of Florida is experiencing a lot of saltwater intrusion, which means if you've got a freshwater well and you pull too much water out of that, it starts to create suction almost and it pulls in the salt water. And so they're trying really hard to put fresh water back into the ground to push that salt water back out. So this has been an extremely successful project, and it's been in place for decades now. Here are a few others in a park location. Again, these are really great because they provide flood mitigation, aquifer recharge, and water quality improvement. Oh, here's another project, the headwaters of the Friends of the Arboretum Creek. And again, so you can see that a lot of them are used for stormwater treatment and flood mitigation. And they provide just a beautiful community amenity. And this is just another view of that water treatment facility. So now Tom is going to talk a little more specifically about the Karcher wetland, an overview of the project and the goals.
Yeah, thanks, Erin. So that was a good introduction to wetlands. Like I said, there's a lot of science and that goes into this and engineering. Um, so Nampa was always looking for a place to do surface water treatment on a non-point discharge. And so we went and started looking around and we found this vacant piece of ground that it's a 27-acre site that's owned by the state, and we entered into a partnership with Idaho Transportation Department. Some of our we call it a demonstration project, but like Erin says, a lot of the elements going into it are all proven technology, but we want to use it for treat surface water instead of drinking water. Also, and just one thing on this, I often get asked, well, why is Nampa doing this project? And well, because we think it's the right thing to do. We're going to make a great community asset. It's going to be very similar to the Albany Talking Gardens. So we'll have trails and we'll have signage for the public to talk about water quality, water conservation, and what we're not actually regulated on this. This is one of the keys of this project is we're just doing this to prove this technology works as a method for us and then others in the state to model on how to handle and treat water from your wastewater plant. Because of our intent on not being regulated, we got some grants from our regulators. So the EPA and the DEQ gave us some funding to help prove out this technology. And it's definitely a partnership project. Like I said, we partnered with ITD. We've got lots of stakeholders, including universities that want to help us with some of the water quality testing And so we're excited about that, and then also document what we learned so we can share that with others. Uh, Another good thing about this is we view this as an extension to our wastewater water renewal plant because if you're familiar with those types of plants, they get large slugs of flow during certain parts of the day when everybody gets home at night and or taking showers, and then it goes back down again. So that's kind of problematic on our reuse plant because we're putting that water into an irrigation canal to be recycled in the summer. So, and that's hard for a canal company to deal with. So this gives us some flexibility to how to manage those peaks. So we can divert some of our treated effluent into this facility, this wetland. Um, so at our wastewater plant upstream treats 12 million gallons a day, and we're going to build this and be able to treat 1 million of that 12 into this wetland. Um, So yeah, here's the site right here. So Karcher Interchange, like I mentioned, it's just right next. Indian Creek is that blue line. It's right next to that interchange. And then 1 mile upstream is our water renewal plant. So that's the 12 million a day. Um, Another thing that was important to us is that we have this be a purely environmental project that didn't require pumping out of the creek to put it to the wetland. So I asked the team to figure out, how far upstream do we need to put the inlet of the pipe in order to hydraulically push all this water through. And it was about 1 mile, and it turned out to be just right next to our plant, which was good because we could put water from our plant right into the wetland pipe, or we can take in creek water if we wanted to, or we can also take in storm water that ends up in the creek that during storm events, and it really gets pretty soupy during a storm event because all the direct discharges into Indian Creek the way that things used to be constructed. Go ahead, next slide, Aaron. So here's our basin. Like I said earlier, we're in Indian Creek, which is a tributary of Boise River, ends up in the Snake. Um, the Boise River is, like Aaron was alluding to, like cold water species, so it's highly sensitive to, and we are regulated, and anybody that discharges the Boise River on temperature and phosphorus. So those are your two that usually, and bacteria. So we're going to look at that at this wetland just so we can prove out that technology. And then, like Aaron was saying, we're going to take to the next step and look at the contaminants of emerging concerns, so the tire compounds and the PFAS and the flame retardants and mercury. Mercury is important too because um, mercury ends up accumulating in bodies of water downstream along the Snake River, like Brownlee, for example, and that's causes a lot of issues with the fish and them absorbing the mercury. So, next slide. Yeah, so Aaron and I are both super excited about the zeolite granular carbon biochar. We're going to have some cells of that and prove out which one works the best for the cost. So we know that granular activated carbon definitely works, but it's kind of expensive stuff. It's about $6,000 a ton versus the biochar is about, and zeolite are about $400 a ton. So we're going to try to figure out what the balance is on which one works best for the cost. It's part of the engineering and demonstration of this project. Um, Aaron mentioned that you can make these carbon materials through pyrolysis, where we are looking at planning a project like in Nampa potentially to do pyrolysis, where we can make our own carbon and put it back into this wetland and reactivate it. So that's the long-term vision that we've got for this facility. Go ahead, Aaron. Okay, so back to
All
Aaron.
right. So this is where all the things I told you about earlier, the free water surface wetland, the subsurface flow wetland, the way the water's applied horizontally, this is where it all comes together. So here's the Karcher interchange right here on the bottom right-hand corner of this image. And this was our first concept. And so you'll see how the design has progressed. But this was the concept by our global constructed wetland technologist, a guy named Mark Madison, who has worked for Jacobs for 45 years. He was a big part of helping restore large portions of the Everglades, and he's just kind of a wetland genius. But it's pretty cool to see this was our original concept with the sedimentation basin, the different cells, and then these polishing cells in white. And you'll see how the design has progressed. But again, it has all those different types of cells trying to accomplish different things, like the temperature, aeration, um, the nitrification, sedimentation, all these different things have been designed into this wetland. But in order for us to design the wetland, we had to do some water quality modeling. We have a proprietary water quality model that we've built based on dozens of wetlands like this that we have designed around the country. We use the results from those in similar ecosystems. And you can see, so there's a lot on here, but we used in our water quality model, we did nutrients and bacteria, metals, and then contaminants of emerging concern. And what I'm showing you here in the gray is the wetland, what we think is going to be the data of the contaminants concentrations going into the wetlands. And what we did is we looked at actual data from stormwater from Indian Creek, and then we looked at the effluent coming from the wastewater facility. So this is actual data. And we compared the two and we took whichever was higher to put into the model. So that 153.6 milligrams per liter of total suspended solids, that was actual data from Indian Creek. Nitrite, nitrate. So you can see these inlet levels, they're fairly high. And then you'll see that with the gray here is with the wetland alone. So this is without the polishing cell. We can achieve 92% removal of TSS. So that's with that sedimentation basin and all the different cells. The nitrogen species about 26%, so it's good but not awesome. A little bit lower with total phosphorus. And that is because a lot of the phosphorus in the system is orthophosphorus, and that's harder to remove. And then you've got coliform. So, the wetlands are great. They do a lot of good treatment, but the thing that is really remarkable is when you add in the extra media cell. So that polishing cell is where the treatment percentages really go up. And because this hasn't been done at scale, we had to use literature-based results. So we did an extensive literature review of the percent removal ranges for zeolite, biochar, tried to look at different combinations. A lot of times for stormwater, entities are mixing these together. So they're mixing biochar with zeolite or, vice versa. They're kind of making a proprietary mix. Because they get better treatment that way. So what we're doing is we're going to be testing different media as well. Same thing happens here with the metals. The wetland alone is moderately good at mitigating metals, some more than others. And like Tom mentioned, we're particularly concerned with mercury. Idaho has a mercury problem because of old mining. And the problem is when mercury is in anoxic conditions, it turns into methyl mercury, which is extremely toxic to fish. So we're really hoping that we're able to have a much higher percent removal once we get the media in addition to the wetland itself. Now, our model did not have, nobody's really looked at these wetlands for PFAS constituents. So again, these are actual PFAS numbers from the effluent of the wastewater treatment facility. All wastewater treatment facilities or water renewal facilities are going to have low levels of PFAS because we, as the consumers, are putting those things into our sewer system. So the sewer systems are passive receivers of PFAS constituents. And so the good thing is we know granular activated carbon is very effective for most PFAS constituents. Um, Zeolite fairly, some more than others. And you'll see here there is a big difference between the long chain PFAS constituents and the short chain PFAS constituents. The shorter chain constituents are much harder to remove. That's why this PFHPA is a short chain PFAS, and so they get, even with this really powerful media, it's harder to remove. So now getting to the design of the city of Nampa. So everything you're seeing here is what we took our CAD drawings and we made computer generated renderings of what it's going to look like. And they are pretty awesome, I've got to say. So you've got the interstate here. You've got Karcher Road here. This is not what the site looks like today, but this is what it's going to look like in the future. The city's hoping to get the funds to build a little parking area, and you can see it's going to have this lovely walking trail, a pretty beautiful, beautiful site. And it's like this little urban oasis, a bridge so that you can access this side of the wetland as well. So all these walking trails, educational signage throughout. So people understand these two right here, these are those settling basins. The first thing, the pipe is going to come in from the right and it's going to go through these settling basins. And then you can see that there are parallel flow paths here. This system up here, there was an existing wetland that was created from a borrow pit when they built these highways. They, had to excavate some material and they left a little wetland. So even right now, the stormwater from the interstate does drain into these. And so this wetland on the northern side of Indian Creek, we're going to be enhancing and putting this trail around. And then this whole section here is completely new. It's not here at all right now. And then this is another borrow pit that we are going to be enhancing and designing. And then the very last thing right here, you can see this is that media cell where the water is going to flow through that media. This was the second variation. I showed you the original concept of the design. This was as the concept was kind of coming to life. And we were starting to think through as a design team, what are all the different features that we want? We wanted to have a log pile here for turtle habitat. Where do we want to maintain the trees and put paredophyte trees? Paredophytes are those that can withstand saturated root systems. Unfortunately, some of the trees might not make it because of that, but we'll be planting new ones that will provide shade. So this is where we really were thinking about the whole project, like the different features to make it a really beautiful and impactful and effective site. And then these are now on the right, these are our 90% design drawings. So you can see how the design progressed. And I tried to put it at the same orientation. So in here, you get the kind of the blue shading, that is the floodplain of Indian Creek. You can see here's Karcher Road, and here's what those settling basins look like. And you can see that there are weirs between a lot of the different cells. The cool thing about that from a research perspective is that we can take samples of the water going in and we can take samples of the water going out of every single one of these cells. We don't have to, but we're trying to create an opportunity for local research to occur. And then there's going to be a bridge and some of the water can be diverted over here. One of the things Tom mentioned, but I think it's worth re-mentioning, is the operational flexibility in that intake. So the intake, so that there was no pumping, just there was enough head in the pipeline to flow through this at the right rate. Again, it's 1 mile upstream. So the intake can take 100% river water or 100% wastewater treatment plant effluent. And Nampa now calls their facility a water renewal facility because we don't believe any water is wastewater. It's all amazing. It's such a resource. But you can see that there are two parallel paths. And like I mentioned, there are 16 locations where we could collect water samples. What I've done here then is on the left is that computer aided rendering. And on the right is the CAD drawing. And what you're doing here is like you're standing and you're looking toward the inlet. So here's that settling basin. And the cool thing is all these different berms are going to have walkways on top of them. So you can check out every single part of this wetland. We want it to be an immersive experience. We've got the bioreactors. Basically, that's that subsurface flow. The media is called a bioreactor. And we've designed it to have the different aerobic, anaerobic, et cetera, throughout, very specifically. Bit.
Uh,
Oh, I think I went back too far. There, we saw that one. Um, So again, this is kind of looking from standing right here along Karcher Road and looking out. Like, that's just another view of the settling basin and the different types of plants. You can see the shade trees. It's going to be just a beautiful sight, but a lot of treatments happening in these first sedimentation basins. And then again, those berms that basically divide the different cells and also serve as walkways. There are going to be 8 foot wide gravel trails. Some of them are going to be 12-foot wide walkways so people can enjoy this beautiful facility. And then this is what the aeration cascade is going to look like. This blue is indicating how the water is going to flow over it into the next phase. So this is where a lot of the photolysis aeration occurs as the water flows from these two parallel paths into this next cell. So I'm basically kind of giving you a tour of the wetland. And then this is the design of that polishing cell. This is one of the coolest parts of the design. This is extremely innovative. This purple thing here, that's trying to show that we have a curtain designed for the middle so that we can put two different media side by side and then test the effectiveness of each. So essentially what's happening then as that water is going to kind of come through this whole cell here, there's some open water, and then from the ground it's going to look like this. I mean, you're not going to even really you can take this trail and look at this, but there's a powerhouse of treatment happening under the surface. So isn't that cool? That's where the media is. And we're going to be testing the zeolite near the creek and the biochar away from the creek. So if you can see here, that's going to be the zeolite on this right side and the biochar on the left. And then on the existing wetland I told you about up here, that was a borrow pit. We're just going to be enhancing it a little bit. We're going to do berms to divide it into two cells, and then some water control structures. And we're really interested in the 6 ppd in this northern wetland because of all that stormwater coming off of the interstate. The riparian corridor is going to be expanded, double its current size, and we've got some very experienced landscape architects who've selected a pollinator species and so many beautiful plants to make this an even more pleasant place to be. Again, I'll just click through a couple more pictures. These are again just kind of aerial views of the wetland system. The subsurface flow, if you remember, when I was talking about the wetlands that don't even look like wetlands, it looks like a solid surface. That's that. Another view of the wetland. You've seen most of these, and then there's going to be a bridge that spans the entire floodplain so that you can access both sides of the wetland system. And that concludes this presentation. I would love to entertain any questions and comments, etc.
Yeah, we've got a couple that have come in, or actually just one in the chat. I guess maybe it's a comment, and I'll just jump to that one as folks are thinking about questions. And then one of the other things we try to do is to solicit comments from the classrooms because it's a little harder for those folks to jump in. So I'll go ahead and just start with the first. questions that are coming in through the chat. One, we have our city of Boise has a wetland park, the Hyatt Hidden Lakes, that takes stormwater runoff to a constructed wetland from northwest Boise to a former gravel pit. Um, can't see quite. Oh, it's a great urban asset. I'm sure most people don't realize the treatment system that removes TSS and TDS from the Boise River. So again, a comment about another system that's out there. I'll jump to the next one, which is how sensitive is the system's performance to seasonal variation in flow or contaminant load?
So that's a really good question. With the seasonal, well, one thing just to note, when we did temperature modeling and we did water quality modeling, our modeling includes the life cycle of the plants, the senescence, like the seasonal, like when they're taking up a lot of plants during the warmer months, and there's a lot of um, life happening, and then kind of the seasonal changes. So wetlands we know are a lot more effective, and sometimes in just regular wetland systems, they can release nutrients at certain times of the year, which is why the polishing cell is such a huge asset because it basically is going to mitigate those seasonal variations in the ability of the plant. I mean, just like any natural system, there are, diurnal and annual kind of seasonal changes in the ability of the plants to do their job. Um, Biological treatment does happen throughout the year, though. It's just the rate at which it occurs slows down. So again, the polishing cell is what we're really excited about, seeing if it can really even out those changes in effectiveness. We do not harvest the plants. That is a kind of an outdated philosophy of harvesting the plants. Research has shown that it's more effective not to harvest the plants and to let them exist kind of in their natural. Once they're established, they kind of maintain their own, life cycle. Um, so yeah, I'm seeing a lot of questions pop up. Do you want me to read them or do you want to read them out loud?
Yeah, either way is fine. I was just thinking, so the plant harvesting question was addressed. There was one up a little bit higher up in the system from Kevin Roche, Boise State, about PFOS sorption. I don't know if you want to just jump to that one, Erin.
Sure. Let me see.
Or I can just jump in. It says,
Oh
how do you
yeah.
anticipate?
Okay.
Go for it.
So how do you anticipate maintaining the PFAS absorption? Okay, so Dr. Roche asked a really good question. Any media can get saturated over time. This media and the quality of water going into it has by the time it goes to the media, we're anticipating it's going to be like in already like pretty high quality. So it's going to take a very long time for this media to get saturated. Um, and when it does get saturated, you'll see breakthrough, just like you would at a drinking water treatment facility. Like you'll see excellent treatment, and all of a sudden you might start seeing breakthrough. We don't anticipate that happening for a long time, but when you do, you will have to scoop that media out and either put new media in, or like Tom was mentioning, if they have a pyrolysis, if they have pyrolysis equipment, they could regenerate the media themselves if it was biochar. Um, I know, like in drinking water treatment facilities, you can regenerate media or you can replace it. I think in this type of natural condition, it would probably be easiest just to replace the media, but it's not going to need to be replaced on like, because this is the first time it's done at this scale, we're going to be really like looking at those breakthrough curves. We're going to be developing the breakthrough curves essentially. But we really just think because it's going to have gone through that whole treatment process before it even gets to the media, that it's going to be like really low levels of these different constituents. And yeah, but that is a very good question. And we have a lot to learn there. That's why it'd be awesome to have some graduate students, doing the data analytics and
There's another following question that was asking what's the best way to stay updated on the project's progress and results?
Yeah, so we certainly contact Erin or I, and we're like Erin said, we're hoping to get some university assistance on some of this, and that'd be another way to stay connected to your your local colleges. So, and then we'll have information on our website as we keep moving this project forward, and various milestones on the projects. We'll be doing news releases. We've had several already when we did the grant acceptance to get the local TVs picked it up. So I think there's several different touch points.
All right.
There's a really good question here that I think we should talk about real quickly is who's in charge of the long-term maintenance? And does your
Yeah.
grant funding support that? The answer is it's the city of Nampa's Park and Rec Department and Tom's group. But Tom, maybe you want to address that um,
Yeah.
funding
So
part.
that's a good important question. So that's we went and investigated some of these existing wetlands in Oregon that Erin mentioned, that like Albany, and asked some of the people that are operating what does it take to keep this thing running. And it's really wasn't much. So there's a little bit of mow a strip of grass near the pathway is about all I heard, but it does, but still we'll have to have you know, litter pickup and all that. So our parks department will end up doing that. We've got a parks department in Nampa. I am going to try to get some funding put into an account that will just so they always have funding for it, so we don't have to rely on our general fund or other sources. It'll be self-sustaining just through interest through that fund.
And one other thing that's really important for a successful wetland project is making sure that you've got the work with a very knowledgeable landscape architect who helps you design a temporary irrigation regime to make sure that those plants get really well established and that they are planted correctly. So we've had projects where we've worked with just like a landscaping company to plant the plants, and the people were not trained how to do it properly, and the plants were planted hastily. Um, and sometimes then you have plants that don't make it. And these plants are expensive and we want them to take root and thrive. So it's really important that you have people who know what they're doing and that they're watered and maintain and until they're really well established, they need a little TLC. One cool thing is that the University of Idaho Master Gardeners program, Tom has been in contact with them, and they were very interested in helping with some of the planting and even just having the oversight of like our landscape architect and then maybe some of these master gardeners who, make sure that all the vegetation gets installed correctly. Because once these plants are firmly rooted and kind of underway, you know, they can be in really good shape. There are sometimes I know in other locations it's rare, but they've had invasive species that were like in the seed mixes, or strange things have happened, and that has to be um, taken care of. But in general, like once these plants are established, they're pretty low maintenance, and the sedimentation basin is one of the few things that has to be scooped out from time to time. But again, until we know the water quality going in is not terrible. So we anticipate, like in agricultural areas, these sedimentation basins fill up a lot more quickly than they will here.
One thing I want to mention about the maintenance of the project. So one of the challenges I've seen on some of these projects is just getting the plants established, like Aaron was talking about. So that'll be kind of the harder part to limit public access while that gets going, because we've seen in spots, especially if they're trying to get near the water, the public can trample it and cause issues with the growth. So luckily on this one, if we're going to build the south side first, so we can limit access on the bridge until we get good establishment, because there's no other access to the wetland besides that bridge to get to the south. So
There was another question that got a little bit buried. It said, what knowledge gaps still exist in understanding how wetlands remove emerging contaminants?
There are a lot of data gaps that exist. We know generally the chemical, biological, physical processes that mitigate contaminants of emerging concern, but they have found that some wetlands without any media can mitigate 80% or like 40% of some PFAS constituents, but they're not really sure how? Is it being taken up into the plant? Is it absorbing to some sediment or to a root? I mean, the actual micro processes happening are very hard to understand. It's because it is complex and a lot of biochemistry is happening.
Yeah, we're just about at time, but I just wanted to see, does anybody in Boise have any questions? I know it's harder for you guys to jump in, or Pocatello if there's a classroom out there. Good. All right. Well, folks, we're right about at time. So again, I want to say thanks to Tom and Erin. Really appreciate everything you've done, and super inspiring and really, really interesting.